Hello, everyone. My name is Rob Quattrochoki, and I'm one of the directors at the Ontario Building Envelope Council. I'm still barricaded at home, as many of you are, and I'm really looking forward to getting a haircut really soon. Thank you for attending tonight's webinar. We are happy to introduce, once again, Dr. Umberto Berardi, who will be presenting on new materials for high-performance building facade systems. Before we begin, there are some housekeeping items I'd like to go over. Upcoming events. As mentioned previously, the CCBST committee is still targeting the fall of 2021 for their next conference, and OBEC has agreed to host the event. The committee is closing in on a venue in Vaughan for the event, and announcements will be made as more information becomes available. Preparations are underway for the 2020 Construct Canada show, and as usual, OBEC plans to introduce the speakers and moderate the building science stream sessions. We're also currently working on a September webinar featuring Cameron Laidlaw and Stephen Quinn of PO Passive House. Watch for email announcements once details are finalized. OBEC committees. Please contact the committee chairs and or members to share your thoughts and if you'd like to participate in their great initiatives. Committee information is available on the website. Call for nominations. The call for the 2020 Anthony A. Woods Award, the Becky, is still active. We know if you know someone who, throughout their career, has consistently promoted better functioning of the building envelope and thereby made a substantial contribution to building science within the context of the building envelope, please complete the online nomination by 4 p.m. September 1st, 2020. Now, tonight's presentation will focus on some of the most advanced building materials available on the market to support a transitioning of the building sector towards high-performance, energy-efficient buildings. Innovative building systems that incorporate nanotechnologies and new materials will also be discussed, including phase change materials with granular and monolithic aerogels and cool retroreflective and thermochromic coatings. Tonight's speaker is Dr. Umberto Berardi. Dr. Berardi is the director of the B-Top laboratory at Ryerson University. His main research interests are related to the study of new materials for improving performance within the built environment. His main focus is on phase change materials and aerogels. Dr. Berardi has published over 120 journal articles and 120 conference papers, receiving over 6,000 citations. He was recently proposed by Ryerson as the first ever Canadian research chair in building science. Dr. Berardi was the chair of the 2019 International Conference on Indoor Air Quality, Ventilation, and Energy Conservation in Buildings, and the International Chair of the Conference on Sustainable Design, Engineering, and Construction in both 2015 and 2016. Dr. Berardi is the editor-in-chief of the Journal of Canadian Acoustics, and he is a member of the editorial board of many other journals, including Energy in Buildings, Sustainable Cities and Society, Journal of Building Performance Simulation, and Building Simulation. Everyone, please join me in once again welcoming Dr. Umberto Berardi.
Thanks, Rob, for the nice introduction. Welcome to everybody for today's live webinar hosted by OBEC, and I really thank OBEC for inviting me again. Today's talk is gonna be about the topic that I'm very familiar, which is the discovering and the application of new materials for high-performance building facades. I've been trying actually to put together a presentation that within 50 minutes will allow you to have a journey over a lot of different technologies. So I apologize for a bit of rush on some of these aspects, and I will be happy to answer any question at the end of the talk or even actually after today's seminar. So we are discussing today a topic of how we can make sure that the building sector tries actually to become more sustainable. We have been repeatedly seeing over the last few years, I would say at least over the last 3 decades, that buildings are a target of any national and international policy when it comes to cut greenhouse gas emission and trying to save energy. And in order actually to have buildings that are acting more sustainably and require less energy demand, really facades are a key element in this spectrum. And we all understand that we are still putting a lot of new buildings yearly, and we are still often putting buildings that, although new building code requirements, they are still not really that sustainable at all. We are still actually, especially in Canada and especially in Ontario, constructing new buildings with technology that sometimes may look innovative, but in reality, they still require our buildings to run, almost 24/7 with an air conditioning system on. Now, as buildings facades have the key responsibility of mitigating the transitioning from an outdoor environment that often is not really friendly into an indoor environment that is supposedly to become as comfortable as possible and so very close to the conditions that people really hope to have. It is a key imperative for building scientists to start understanding what we can do in order to behave and to act for building a better and more sustainable Toronto. Now, the huge majority of new towers that we daily see coming up in Toronto, across the entire Ontario and across the entire country, really offer us an opportunity to deliver a new way of constructing. And today, I'm going to present you a bit of the sense of this scope, which is framed within my lab and within my group. The group is really a zero energy building group, and we often work on new materials. And today I'm going to present some of these new materials, and specifically speaking, I'm going to focus on some of the application of these new materials. So first of all, let me introduce you with the outline of today's talk. I'm going to actually speak about 5 different main categories of innovative products we can use in buildings. Now, these 5 different categories will correspond to the 5 dots that you see at the bottom on the right of each one of the slide. I'm going to start on phase change material, and I'm going to really introduce the importance of buildings facades that have the capacity to accumulate some energy and have some thermal mass behaving action. I'm going to then move into materials that have a very low thermal conductivity materials, and I'm going to introduce you to the world of super-insulating facades, which are not necessarily those facades that are 40 or 50 centimeter thick, or that we often see in a lot of construction that are targeting sustainability, but are actually facades that in a couple of centimeters are able to really guarantee our value of 20, 30, if not more. I will then move on to the world of new forms, and I'm using actually the forms to also introduce a key topic of today's talk, which is the embodied energy into building materials. So although it's not necessarily the focus of today's talk, I'm going to actually give you a snapshot of what it actually means for a material, not only to be sustainable, but also to be able to be reproduced with a low embodied carbon. And then towards the end of my talk, I'm going to focus more specifically on coatings. I will start at point number 4 on reflective, cool, and thermochromic coatings. And I'm then going to finish and wrap up today's talk with a short discussion about selective coatings for Windows systems. So again, you see in this kind of slide, the outline of today's talk, 1, 2, 3, 4, 5. We are all speaking about materials that have a kind of a size of a few micron. They often may actually almost be included into the world of material science. But today I'm going to propose you how material science discoveries and new products can help the building sector to become more sustainable. I'm going to start actually from the possibility to approach thermal energy storage within facade. Now, we all heard, over the last few decades, if not even early, the critical importance of thermal mass. Somebody called them thermal capacity. And the specific meaning of this is that we can have a building with is a lightweight construction and has oscillating temperature as the one that you see in this graph with the kind of green wave that goes up and down as these actually kind of characterized by waves that are significant. But if a building has a significant thermal mass, and so you can see in this graph, the blue line, what you're able to achieve is an oscillation of internal temperature that is not really significant. And typically you also see a delay in the peak that you can obtain in maximum temperature or in minimum temperature indoor. Now, from a strategic point of view, having a building that acts as a material, as a building with a high thermal mass, it's important, and it is particularly important in Canada, as well as it is particularly important worldwide. However, historically, building codes have not really paid almost any attention to thermal mass. The majority of construction sector has been typically putting codes that only target the R value, the thermal resistance of the enclosure, and not necessarily have given enough importance to the value that having a facade with a given thermal mass may represent to avoid overheating in the middle of a kind of a summer heat wave, as well as actually the risk that we can suffer in the middle of a winter night. So it is important to understand that although building codes often do not push us to have significant thermal mass on the facades, dynamic simulation as well as daily behaviors in these buildings have really proved us the importance of thermal mass. Now, why don't we not use daily thermal mass is because the building sector is often pushed towards lightweight construction, as often pushed towards prefabricated facade modules, and all these elements are really missing thermal mass behaviors. So I will say the construction sector has moved towards a technology that doesn't have this thermal capacity, and here we come. Here we come in the sense that new materials may provide, without really giving you the weight of a brick wall, of a concrete masonry unit wall, still the capacity to obtain a significant portion of thermal mass, so still a capacity to have a thermal energy storage. Now, if I want to kind of characterize the possibility of a building, or in general speaking, of a system to accumulate energy, typically, historically, we are using sensible heat storage. The sensible heat storage is the kind of heat storage that Casa Loma does in Toronto. You enter into a cathedral in Toronto, you instantaneously feel that it's cool in the middle of a summer heat wave. And the reason being is that there is a huge thickness of stone that will require a lot of energy and often a lot of time before it can warm up. If you do the same thing in a glass tower that we are building downtown, really, as soon as it is, sunshine, and as soon as you start getting into the mid of the day, internally you can easily reach 50 degrees Celsius if you don't turn on your air conditioning system. So sensible heat is an option, but clearly we can build high-rise buildings with stones as it is in a cathedral. We can really afford the technology and the cost of having, a meter thick wall, even when we are putting an high-weight construction. So a different approach is to use latent heat storage. Now, the latent heat storage, which is often used in air conditioning systems, for example, in those systems that have an IC storage, it's basically a storage that uses the property of a material to change the phase. And here it is actually the value of phase change material. Every single time we have an ice bucket and we require to this bucket to basically phase change from being a solid into a liquid, or vice versa, from a liquid into a solid, we really have a huge potential to store a huge amount of it. Now, I don't want to speak about the physics of the phenomenon, but if you actually follow me for 1 second and you see this glass of water and you start seeing that kind of bucket of ice getting into the water, it's important that you get the sense that there is the same energy that is needed to a nice pocket to basically melt that there is for the same amount of water to move from 0 to 100 Celsius degree. And this really gives you the value of why thermal storage is critical. To break the bonds of a solid structure into a melted liquid structure, you really need to invest a huge amount of energy. And vice versa, if you want to solidify this in that kind of solid layer, you can really make sure that you have the potential of a huge thermal cooling energy storage. Now, this is possible and has been possible with what we call the phase change materials. Some of you may be curious about what they are. They're typically nothing more than a wax or a kind of almost a water. In reality, we will see in a moment that it's not really necessarily a pocket of water, but the principle is very similar to the material that we typically use for candles. So you have a material that is solid, and when it gets quite hot, it can become liquid. And this phase change, it's critical to act as a thermal storage with a huge thermal mass capacity of storing heat and avoiding in our building becomes extremely hot. Now, here there are a couple of important aspects that I need to remind you. The first actually aspect is that as in building sector, we want facades that are solid. Nobody is stupid enough to pretend that we want facades that can become liquid. So phase change materials have been always suffering the critical risk of being compartmentalized into plastic bags. And often in the past, in the 90s and the early years of this century, people have criticized these products because you could punctuate these bags, and this punctuation could result in a leaking wall or in a leaking, kind of false ceiling. But right now we have solved these problems. And I'm going to show you in a moment how we solved this problem. The second element of consent, and I want to make sure that we all are familiar with, is that although we often speak about phase change material and we use the singular word material to specify PCM, in reality, there are thousands of different PCMs, and one of the critical elements when it comes to thermal energy storage with PCM is to get a very good understanding of the different phase change material that you can desire to adopt in your building facades. So first of all, let me actually introduce you with this huge family of products. Here you see a graph where you have the temperature at the bottom and you have the melting enthalpy in the vertical axis. So the y-axis tells you how much energy you can store in this material. And clearly, typically, the more the better. Because if you have a higher melting enthalpy, if you have a higher storage capacity, then you don't need to use a lot of phase change material. So typically, as soon as we can use materials with a melting enthalpy of 4, 5, 6, 700 kilojoule, it's good. But unfortunately, not a lot of products offer that property. You also can see in this graph that, basically we have materials that melt or solidify at a temperature that can be, minus 400 Celsius or plus 400 Celsius. And we clearly do not really need these products because they are not typical building facades. They can be useful in some application for some mechanical systems in specific industry, but not really for building application. So in building application, our facades typically withstand anywhere from 0 to 50 degrees Celsius. And so you really need to stay in the wall that is typically characterized by paraffines or gas hydrated. Sometimes we can use salt hydrated as another option, but really we don't have a lot of different products we can use. Although I need to actually stress another aspect, that even the world of paraffines, for example, which is a very common PCM world for building facades, it's full of a lot of different options of paraffin. So it's not really a single product, but you need to start getting a good sense of the different paraffins to be useful in your building facades. Now, going back to one of the questions I was mentioning you before about do you ever think about putting a plastic bag that can punctuate it and can melt? And clearly the answer was not. I said to you that we have discovered how to introduce PCM in buildings. And the process that currently is the most common and pretty good to be delivered is by basically microencapsulating this PCM in a polymer shell. So typically on the market, you can find a lot of pounders of PCMs that are really surrounded in a polymer. So at the end of the day, you are using nothing more than a sand or something that looks like a sand. But if you start using a microscope and you kind of zoom in, this sand, this granular pounder, is really encapsulating in the middle a PCM. And so the PCM can melt and can solidify, and this process may accumulate temperature or release energy or accumulate or release energy. Meanwhile, it's stabilizing your internal temperature in the building, and can be your thermal battery, although it's pretty lightweight and although it's not really kind of increasing the weight of your facade too much. Now, these pounders clearly can be done with a lot of different PCMs, so the selection of the right PCM is critical. But also, we have been seeing a lot of new pounders and a lot of new building products coming up on the market, as well as a lot of first attempts to monitoring thermal energy system in some real buildings. And I'm going to show you in a moment a few of these options. Let me first introduce you to some of the topics that are available on the market that are representing option PCM's products. Here you see, for example, some gypsum boards. What they are, they're nothing more than, kind of traditional gypsum boards, or at least they look like traditional gypsum board. But in the gypsum, there is also some pounder of PCM. And as you can see, you have the capacity to start storing some energy. Now, if you see the fifth column with the latent heat of fusion, you can also realize that typically in a lot of this product, the thermal mass is not huge. You don't have a huge capacity of store, a huge amount of energy, because in reality, here the PCM is mixed with a lot of gypsum. But it's still better than nothing, and it still is a way to, give to a lightweight element in our building facades, such as a gypsum board, a thermal function, which is basically the value of stabilizing the indoor temperature of your building. You also may start seeing in the fourth column that a critical factor is the melting temperature. And I've selected in this table products that have a melting temperature between 20 and 27 degrees. And there is a lot to say why these are critical and why these are, useful temperature. And I'm going to show in a moment why these are typical temperature we use. Let me first give you another snapshot of possibility to use PCMs in buildings, not only as a gypsum board, but also for concrete tiles or ceramic tiles in your kind of flooring. Here you see an house I designed a few years ago. And in this particular house, we used one of those powder, specifically speaking, the micronal PCM. And we mixed this powder in a 13% by volume in the concrete tiles that were used for the pavement of the house. So if you see on the top left image in this slide, you see these concrete tiles. They were basically put at the end of this lightweight construction, fully glazed. So a house that was, eventually taking significant risk of being extremely hot in the middle of a sunny day. And here you see on the right with the red curve, the temperature profile of the house without a PCM. And you can see as easy it was to reach 35, 36, 37 degrees in one temperature, in temperature in 1 week. And then you can see at the bottom, a following up week with completely similar outdoor condition. But once the PCM concrete floor was introduced, then you start seeing this stabilizing temperature profile, which doesn't really go too up into the sky, still, hot enough to require an air conditioning system, but it's clearly way easier to cool down a building that is only at 30 degrees than to cool down a building that has reached 37 or 38 degrees. So where is the value of this PCM? The value of the PCM was in shifting the amount of solar energy that was entering this house and moving, the maximum peak in temperature from being in the middle of the day towards the night, where the night cooling effect with a bit of cross ventilation was enough to cool down completely our house passively. So at the end of the day, what I'm actually showing with the blue curve was basically the profile of an house where we only used cooling overnight without any air conditioning whatsoever, and we were still able to guarantee, a relatively speaking comfort level, or at least a better, starting point for reaching comfort level than a scenario without any PCM into the house. Going back to those kind of gypsum boards with the PCM in the middle, and they're actually value for even retrofitting application in order to increase the thermal capacity of an existing building in which you can put some gypsum board with PCM. Here you see a project done with a developer in Toronto 3 years ago, where we basically started monitoring in one of his towers some units where we were putting this gypsum board with PCM in different units for different orientation, and we were using side-by-side units to start playing a bit of comparative assessment of the indoor condition without any air conditioning system. Now here you see a bit of the results, and I'm not going to go too much into the detail. At the bottom right you see the link to the paper in 2017 that was published with all these results. But basically for Toronto, so a condition of significant value for us, we were able to obtain results that were enough to guarantee a cut in the energy demand that was always oscillating from anywhere in the 12-13% up to 23, and in some cases up to 30% of the energy demand compared to the baseline without this kind of gypsum boards. Now, a critical element that I also want to stress is that you also realize that the orientation of the facades and a few other configurations are critical when it comes to these materials that are so material science based. So they are not easy to use material, but they can be particularly useful. For example, this is another house built in the northern part of our country, and here you see a construction that used the concrete floor as a thermal battery, almost as a kind of a thermal storage element in order to cool down or heat up the house and use the critical mass of the concrete floor. Now, in this particular building, later on, we actually tried to do some X amount of research. And more recently, with the local company, we have been coming up with a system that basically use the whole of some concrete blocks to enhance them with some PCMs. And so to basically give not just a structural value to these elements, but also huge thermal battery to these elements. Now we've been doing work also, for example, with coupling different PCMs and using PCM with different temperature. I said you before paying attention to the temperature, and the reason why I was telling you that is because the PCM does this kind of phase change transition, but it's critical and important to understand at which set point we typically use our thermostat. And a good starting point for saving energy is probably to have different setting point for heating and cooling, and particularly to have cooling season, temperature set point in the range of 24 to 27 degrees, and probably heating season from 20 to 22 degrees Celsius as set point of your air conditioning system. So specifically speaking here, we have been working on coupling different PCMs and making sure that we can use some PCM more effectively in summer and some PCM more effectively in winter. We worked on bio PCM, which are kind of quite common these days in North America because they have a very, very low embodied carbon energy. They are basically waste of other industry, typically pork industry and other animal oil industry, and they have quite good property for storing energy. And so there is a huge amount of potential in these products. We also been working with some new nano PCMs, a bit more technically, still be not really close to the market, but tune your eye because in a few years these could become very popular materials. Now focus on the second point of today's talk, since we only have 1 hour, and I want actually to start introducing you to the world of super insulating materials. I started today's talk by saying that unfortunately or fortunately, building codes have often put all the attention just on the R value of the facades, and not really a lot of attention on the thermal capacity or thermal mass behaviors of our facades. So when it comes to the R value of our facades, we have seen over the last almost 50 years since 1973 and the following up codes after the crisis, that building codes have pushed us to design buildings with an R value that is bigger and bigger and bigger. And some approach to address this challenge is by basically putting thicker insulating layers. Now, while this is an option, and for some application can be a good option, especially if you are looking of an isolated construction where the thickness of the wall is not critical, it's definitely not an option when you are designing a nice rise building in the middle of a metropolitan city. And you cannot really afford the challenge of having very thick layers of your insulating element. So luckily for us, we have new products that are typically under the category of super insulating materials. And I'm going to specifically speak today of aerogel, but also there are vacuum insulating panels that are becoming, again, more and more common for the building sector that often are giving us the opportunity to have a very low thermal conductivity. We are almost speaking about material with a thermal conductivity of 0.01. So we are literally speaking about materials that have a thermal conductivity that is a quarter of the thermal conductivity of a fiberglass, which basically means, in other words, that you can have the same thermal effect with the quarter, so with a fraction of the insulation thickness you will have to use if you're using a mineral material. But clearly, this new potential and these new materials still have some challenges that I'm going to present to you today. So what is an aerogel? So an aerogel is basically a material in which you have trying to eliminate from a gel all the liquid portion. And they're often, kind of described as frozen smoke because in reality they look like a frozen smoke. So these are very lightweight material. They only, weigh a few kilos for an entire cubic meter. They have, 98, 95, 99 in sometimes percentage of voids, and they have a low thermal conductivity of only 0.01. So how do you typically obtain these characteristics is by basically a chemistry process, which unfortunately makes this product quite expensive. And this process starts from a silica gel, very similar to the gel you may be using in your air. And then it basically evacuates in under specific characteristic and condition all the liquid portion of the gel. So just to give you the sense of the way in which these materials work, imagine that you have on the left a photograph of a fiberglass. And imagine that what it is depicted in this figure is basically the void into a fiberglass of a mineral wall. So although we speak about a void, in reality, we have molecules of air. And even if you are speaking about a foam, a closed cell foam, you still have a blowing agent that is there as a gas. And this gas is moving around. And by moving around, can move heat from one side of this square to the other side. So although we typically consider an insulating product a material that is fully solid, and it only has a thermal conductivity that is only acting for conduction, in reality, in the cavities of these products, in the voids of these products, there is convection happening. And if the void is big, convection is more significant. And here it comes actually the aerogel. The aerogel is a material that has this very strange chain structure that basically prevents to the red bubble to move a lot and to be limited to this structure. And by doing that, the convection within the porosity, within the cavity of these insulating materials, it is limited. So basically, the red balls could now really move effectively and fastly, and so convection really gets almost limited to zero into an aerogel. Now, if you take this aerogel, and I showed you previously some of these kind of particle of aerogel, now you can put these aerogel granules in any material that we typically use in building construction. You can put in cement-based mortar concrete. Now, it's not necessarily, I will say, an easy approach because clearly you are using a material that still has a quite high cost into a material that has, a generally speaking, low cost, and you are putting a super insulating material into a material that is renovated not to have a very low thermal conductivity as a concrete, but it is a good option to, for example, moving forward, imagine that in the years to come, we can start having concretes that are also having a low thermal conductivity. And to be honest with you, we have already created concrete blocks with thermal conductivity in the range of 0.08. So we have already created with these mixes of aerogel and concrete some blocks that are low in thermal conductivity. More importantly are the opportunity to use these days gypsum boards with aerogel, blankets with aerogel, or plasters with aerogel. These are all products that can be created with thermal conductivity below 0.02. So still, basically values that are significantly lower than fiberglass. And they can be effective and useful in many different applications. They don't suffer a lot of aging. They, thanks to the fact that the aerogel typically is odor repellent. They also have good behaviors when it comes to the fact that they do not really get wet. So hydrothermally, they are good products. And in fact, aerogel-enhanced blankets have started being more and more common, for example, for protecting thermal bridges in specific construction topology. What is an aerogel-enhanced blanket? An aerogel-enhanced blanket is basically a normal blanket as a fiberglass or any actually fiber material in which you were basically putting a lot of the gel when it was still liquid, and then you are evacuating the liquid portion. And so the structure of the aerogel gets basically trapped into the aerogel bonds of the fibers. So these products are available on the market, and they are produced by a lot of different companies. Here you see some of them. There are more companies that have started producing these products. Some of these products come from startups. Some of these products come from more well-established companies. But one of the important characteristics of all these products is that their thermal conductivity is often not too far from 0.01 watt meter Kelvin. So they have a very good thermal behaviors, and we've been testing this kind of material properties in our lab. I need to confess that for some of these products, we found results that were basically higher than what those companies were declaring in the technical sheet. But without actually questioning, these products have a very low thermal conductivity compared to a lot of other products. And they are produced and sold these days as tiny layers of 1 centimeter or 50 millimeters or 20 millimeters that you can use a lot, for example, for protecting thermal bridges. As a matter of fact, just to give you an example, last year a student of mine studying and performing some modeling of a lot of typical thermal bridges risk and issues in both concrete and steel construction. And if you are interested in seeing some of the results, there is an article in the OBEC publication of last spring that really shows all the building details with aerogel blanket protection and without the aerogel blanket protection. So you can see, as for example, a concrete balcony detail by simply putting 1 centimeter thick aerogel blanket avoids to really, have the traditional effects of the concrete balcony. Similarly, also a concrete shelf angle detail will really be resolved very nicely once you start protecting that kind of concrete element with an aerogel blanket, and so on and so forth. I don't have time actually to go into the details, but really you have plenty of opportunity if you go to this Pushing the Envelope Spring 2019 issue in order to get a sense of the opportunity that aerogel blankets provide to us. And specifically speaking, we also have used that opportunity to run some simulation of the potential value of extensively used aerogel blankets for protecting all the thermal bridges existing in both concrete as well as in steel buildings across the Canada country, so across different kind of zones from zone 5, 6 to 7. And you can see that there are significant energy saving that, in some cases it can reach up to 20, 30 kilowatt hour per square meter by protecting all the thermal bridges with aerogel blanket. So clearly, in order to push our facades, our envelope, to really promoting the possibility for wire enclosure to become fully a part of a desired trajectory towards zero energy building, these options really represent a significant additional value for building facades. Now, aerogel have been used also not only for blankets or for plastics or concrete, but also, for example, in window system. And they've been used, specifically speaking, both within, kind of glass units, so into, the real transparent portion of the window, as well as they've been used recently in the frame. And we all understand that the frame is still the most critical part that we have to face when it comes to high performance windows or curtain wall. Because at the end of the day, we can still put the triple or quadruple glazing window, but in reality, a lot of these windows, they are still really supported by frames whose thermal conductivity is still remaining quite high because they're often metal based. So aerogel into the cavity of a traditional curtain wall can represent a good option to cut significantly the thermal conductance of the frame. And here, in fact, you see some of these products. Again, no time to go into the details. Plus, there are new products currently on the market since I put together this table. But I want to show you this to give you the sense that we have some products that have already started introducing aerogel in glasses systems. They're not really common in our country yet, but they're definitely actually a topic to be focused on, specifically because we are still looking at construction with a huge portion of transparent enclosure or curtain wall facade design. Now I'm going to move into the third spot of today's presentation. I'm going to speak about new forms for building facades. Now, indirectly, I started the discussion of this topic last month at the webinar when we were speaking about the importance of effective thermal conductivity behaviors in real kind of facades. And I was speaking, if you were part of that seminar, about the implication of, for example, different temperature or different relative humidity may have when it comes to the final effective thermal conductivity of our insulating products. Today, I'm going to specifically focus on foams, and the reason being is because foams represent a good compromise these days between, a traditional insulating product and a super insulating material as the aerogel of the VIP. They have actually a thermal conductivity that often may be at least, certified with a value that is below 0.03 watt meter Kelvin. Sometimes they almost approach 0.02 or at least 0.025 watt meter Kelvin. So foams have, really good potential for some specific aspects. But we also understand that they've been often claimed as material that have a high embodied carbon, and they have been actually often be accused to be material that are not really sustainable. So today I'm going to actually just give you a snapshot of the fact that this statement is probably not fully correct, or in other words, it is a bit out of date. It is true that in the past, foams were often produced with material that has some environmental issues, but it's not necessarily true for all the products that currently we have on the market. As a matter of fact, and I apologize for this long text that you can read at the end of the talk, but what I want actually to certify to you, being in the world of research for some good amount of years, is that foams have changed quite a lot of the last 2 or 3 decades. After the Montreal Protocol, they were accused as materials that had a huge ozone depletion potential. And reason being is that they were producing with a blowing agent that with the time was escaping the foam matrix. And they was eventually responsible for the risk that our ozone protection layer had for many years. Now, a lot of these foams, if not all of them, have now almost moved to zero the ozone depletion potential. So the ODP of new foams, it's pretty low. But sometimes people do not really pay attention to the fact that some of the foams of a few years back, they still had a significant greenhouse gas emission factor. They were still not really highly sustainable. They have still some level of high embodied carbon. And so the industry over the last few decades has been pushing not only to make sure that the ozone risk was resolved, but also that the greenhouse gas emission factor of the production of these firms was resolved. As a proof of the fact, they moved from the first generation of CFC, chlorofluorocarbons blowing agent, into the second generation with HCFC, and more recently they moved into the HFC, so the hydrofluorocarbons blowing agent. And a lot of new foam companies and products are already actually ready and up to speed to present products that are the 4th generation of blowing agent. So they use hydrofluoroolefins, so HF4 kind of blowing agents. So new blowing agents that typically have a much lower embodied carbon. Now, to put the number and also to support what I'm saying, you can see in this graph as a lot of these systems and products move from a GWP, so a global warm potential, so an indication of the risk of carbon emission associated to these products, of a few thousands for the first CFC, the first generation that you see into the 3rd row of this table, down to levels that were a few years ago into the range of a few hundreds. And recently we start having materials that have a global warm potential of a few numbers like 10, 20. And also we start seeing material that, since they use CO2 as a carbon dioxide as a blowing agent, they literally have the global warm potential of 1. I remind you, if you're not really familiar with this coefficient, that the GWP is basically a benchmarked, I will say, metric that compares the blowing risk, sorry, the greenhouse gas emission risk compared with traditional carbon dioxide. So if you use carbon dioxide as a blowing agent, you are basically benchmarking it yourself. And so the GWP of some of these products, it's basically equal to 1. So we have already low embodied carbon foams. It is, our responsibility as building scientists and as professionals into the facade building system world to start pushing for higher adoption of these products. And the value of these products is also that they have solved, or they are almost solved, a lot of the troubles, as I was mentioning last month, of risk of effective thermal conductivity that is different from the nominal thermal conductivity on the technical sheet. And the reason being is that these materials have AJ risks that are quite lower than the first few CFC blow-it agent foam. The reason being is that a lot of these kind of closed cell foams do not have significant risk of this kind of blowing agent to escape from the foam in the same amount that we were used to have in the past. And I don't want to spend too much time today, but if you go back to last month's seminar, or you read some of these papers that you see always at the bottom right of my screen, there are some papers we've been doing in order to kind of prove that even when you take into account the effective thermal conductivity of some of these foams, you can still be in a situation where the real behavior of the material is quite consistent and quite similar to the nominal value. They still need to be carefully considered, especially when they are used, in outdoor condition at extremely low temperature, and they are, polyisocyanurate products. But clearly, this is, a topic for another talk and not for today's talk. I'm gonna move now towards the fourth pillar of today's talk, which is the topic of coating, cool materials, and reflective facade elements. Now, we are all familiar with the implication of the climate change. We're also all familiar more and more with the implication of the risk of a microclimate in our cities that is quite different from the climate that we had outside the downtown core of the city. And we often speak about the urban Italian effect as the merge of all these kind of microclimate implied effects that we can see in the downtown core of a large city. And in order to face this kind of challenge, more and more often we start seeing the value of cool materials. Now, historically, I would say this wasn't really a topic for Ontario, because historically cool coatings, reflective coatings, have been significant portion of attention in cooling dominated climates, and so clearly not in Ontario that is an heating dominated climate, or at least used to be only a heating dominated climate. But the more we start facing the challenge of climate change, the more we start facing the risk of overheating inside our buildings, the more we start seeing the implication of heat waves in a country and for a population that is not used to heat waves, the more even building codes have started pushing, cool coatings. And we're all familiar with, the tier 2, for example, in Toronto, and implied request of a cool coating or an High-albedo coating for our roofs. And we are not in in a Greek town, and we are not yet used to kind of facades that are fully white. But we have understood that, specifically speaking, cool materials may provide a good value to reflect back towards the sky the extra solar energy that may heat our facade. It may increase the temperature of our facade in the middle of the summer, and we may not be desiring that kind of effect. Now, first of all, you need actually to be aware of the fact that material science these days is able to propose to you cool materials that are not necessarily white. and is able to propose core materials that may be of any color you may desire. Here you see, for example, in the top right side of the screen, some material with an albedo, so with a ratio of the energy that gets reflected and gets absorbed, that is different from the top and the bottom line of the materials, although the colors are very similar, and although a lot of those materials are now really super white. And in fact, we have been seeing these days a lot of new reflecting materials and also a lot of retroreflecting materials. So material that also not only reflect outside the energy is arriving, but reflect with the same direction of the incoming light. So instead of reflecting against the opposite building, and instead of risking that you're not getting that energy, but the opposite building across the street is getting all that energy, new coatings have been able to kind of use material science nanospheres in order to retroreflect that energy back into the sky. Now, just to show you what that means, it means that basically instead of reflecting in a channel of, basically a downtown condition in which two buildings face one against the other, instead of reflecting back against, the street, and so getting more energy at the street level, or reflecting against, the opposite building, these materials are able to reflect back towards the sky. Now, clearly, retroreflectivity and, typically speaking, cool materials, and clearly retroreflectivity is more valuable for facade versus cool materials are fine often for all roofing applications, are still a question of discussion for Canada, to be honest with you, because you really lose the gain that solar energy will have been eventually able to provide to you in the middle of the winter. Now, one opportunity to actually look at this is that instead of using retroreflecting materials, is these days the challenge and the opportunity of using thermochromic materials, or materials that have an albedo that basically changes depending on the temperature. What that means, it means that you can have products that have two effects. They typically have an albedo that is higher at higher temperature. So in the middle of the summer, when the facade becomes actually hot, then the material becomes reflective. But when the material is kind of cold in the middle of the winter, the material still retain all the energy that is arriving from the sun. It is more or less the same principle that we use in thermochromic windows, or that we have been using for almost decades so far in transitioning glasses. So the fact that the material can change the transmissibility according to other factors, it's a potential huge value for dynamic facade design that we haven't yet fully explored. So here you see a recent publication of a PhD student of mine, Shada Sodian, and she has been working on thermochromic coatings and a bunch of these products and pigments for facade application. I need to confess that we have still some extra research to do in order to come to a fully explore value of these coatings, but there is definitely a lot of value in these products. And in fact, we are ready now to start a pilot project within the Ryerson campus, where we are basically painting a facade with a thermochromic element, and we are going to actually start monitoring how this material behaves in the real field. Last but not least, I'm going to just describe over the last couple of minutes a bit of coating or high-performing coating for glasses. And specifically speaking, since we don't have a lot of time, I'm going to focus on coatings that are low solar gain. So these are basically coatings that are already valuable option, not only for new glasses, but also for retrofitting your current windows. Whenever you have the challenge of having a facade that is gaining too much heat in the middle of the summer. So clearly this requires that you get an understanding of the implication of the light transmission that a glass has at different wavelength. And typically what you need to understand is that why we want to have a glass as transparent as possible into the visible range, so the range from 300 to 800 nanometer. We also don't want often that kind of transmission to occur in the infrared range, where a lot of it may arrive and that it may not be actually valuable, especially in an office building, especially in the middle of the summer. So there are products these days, and here you see, for example, one of them. They can be applied also in retrofitting. They're almost fully transparent. They can come as, kind of pellicola. They can come as a liquid coating to apply. That have the possibility to transitioning the transmission of your glasses. And you can get a sense of this into a couple of papers that I'm gonna mention at the end in the reference of this talk. But basically, these are coatings that are almost fully transparent into the middle of the visible range, so they still remain quite transparent. They don't have a lot of coloring, a bit of blue, not too much, as you can see, in the range of 400 nanometer. But then they have the opportunity, still with a very high color rendering index, so a perfect vision of the outdoor, a perfect perception of the outdoor, to really cut significant the transmission of solar energy. From the condition of a clear glass that basically allows your glass to almost bring inside your building over 80% of the incoming energy, into values that can be as low as 40 or even less than 40% of that incoming solar energy. So I hope I've been trying to give you an overview as much as possible in an hour of a lot of new products. There is still a lot of work to do from our side at the research world when it comes to technology transfer. There is definitely a lot of work to do when it comes to pilot projects for new facade. But we have a lot of new products, and a lot of them are very close to the market. And as a proof of the fact, we also have been starting showcasing some of these products, for example, in expos such as Construction Canada, just to give you the sense that these are products that you can start, considering for your next facade. I thank you for your attention, and I'm more than welcome to receive any question.
Thank you, Umberto. We have a couple. Well, one is a comment and one is a question. So I'll start with the comment. I would like the audience to know that HFC blowing agents are being banned at the end of at the end of 2020 in Canada. This will force all spray foam and XPS manufacturers to change to HFO or other low GWP blowing agents. It also means all specifiers must change their specifications to include references to HFO, low GWP, and new product names. That's just a comment. I don't know if you want to add to that at all, Umberto?
To be honest with you, my European background has told me that, and this is an extra comment. The comment that you just read is correct, but also I like to say this is true when the clock down is arriving and that transition happens. Because it is true that there is, I will say, an expectation that we will fully go into the fourth generation of foams in the near future. The near future should be in the next few months, but we also don't know what's happening with a lot of challenges that we're facing these days. If some policy request gets released as a kind of a post-COVID, for example, plan or other related aspects. So there is definitely a trajectory to move into a fourth generation. Likely can happen already at the end of this year. If not, may take a few extra months, but it is in the pipeline.
Okay. The next question is, when using PCM in core slabs in buildings, what is the impact on fire, sound rating, and smoke sealant for plumbing stack penetrations?
Okay, so clearly, I hope you got the message that it's hard to speak about PCM without referring to a specific PCM, first of all, because different products may be different. So paraffines are more smoke issues and implications that, for example, some salt. Okay, they are both PCMs, but their implication is different. Typically, the research has been now working on establishing polymers for the microencapsulation of the PCM. They basically resolve all the issues of the smoke. So from the point of view of the smoke, we have solution. You basically need to to be aware that you will be forced to use specific polymer and not others, and so on and so forth. When it comes actually to the sound, I don't think actually there has been any studies so far whatsoever worldwide. The variation of the sound insulation of a concrete facade or a concrete floor for the effects of the PCM. Now these are additive. They give a bit of extra porosity to the concrete. So I may expect the result to be leading towards a more significant sound insulation into the high frequency and less in the low frequency, since the concrete loses some mass. So the mass load will not apply in the same, then the porosity will help you into the high frequency range. But nobody has been doing any study as far as I know on this topic, and I also don't think that this is really a critical element, especially as we all know the building code of Canada doesn't require actually sound insulation of our floors. So it's also a bit of a chicken and egg problem to pretend that we have solution that fits everything. And when it comes to acoustics, if as soon as you start adding a layer like a kind of a carpet on a concrete, or a kind of another finishing layer, then the entire acoustics behaviors of that system is completely different.
Okay, great. We're a little bit past the hour. I just have a quick question myself. You kind of answered it, I guess, but you mentioned about the new closed cell foams that will have a carbon dioxide as the blowing agent. I just wonder how far away they are from going to market, and I guess that's tied to the fourth generation adoption. And do they achieve the same or similar effective R values as the traditional closed cell foams?
So I haven't yet. Oh, actually, I have done some tests, and I should say, but just with a couple of products. I mean, I've seen that they have been able to obtain good value of thermal conductivity. So effective R value is similar as the third generation. To be honest with you, the reality is it's hard to generalize until you start getting the sense of which products hit the market, because a lot of these blowing agents are under patent, proprietary, industry. A few industry and global industry in the world detect and basically drive the market towards specific direction. And so blowing agent is a kind of a strange market where often the final manufacturer you have on site, it's dependent on the blowing agent and a multinational into another country as basically provided as a blowing agent. Having said that, I've done some preliminary tests. Results are somehow promising. They seem to be as good as the third generation, although I will still wait myself to do a few extra tests with a bunch of different products before being able to scientifically say this is the case. It's also true I haven't done tests over the last 6 months since the lab has been closed, unfortunately, for the COVID. So I'm looking forward now to restart a bit of lab experience to start also gaining more insight into these new products.
Great. Well, I'd like to once again thank Dr. Berardi for a very interesting and informative presentation this evening, and I'd like to thank everyone for attending. Please keep an eye out for news on our next webinar to be held in September. Until then, stay safe and enjoy your summer. Good night.